All right, so thank you for the invitation. It's really exciting to take part of my afternoon to come over here and talk to you all about some of the work that we're doing. As Ava said, I co-lead a couple of things at Google. One is this team called the Big Picture Group, and a lot of our work centers around data visualization. In the last 3 years or so, it's been very much focused on data visualization for machine learning. So you'll get to hear a lot about what we do today. I also co-lead the PAIR initiative, which stands for People Plus AI Research. And there, we have a bunch of different kinds of things that we do as part of this initiative. We produce open source software, hopefully some of which you are familiar with. TensorFlow.js, anyone? TensorFlow.js, yes? Yes, I'm seeing some nodding here. We also put out educational materials. So some of this actually starts to overlap with data visualization for machine learning. We've noticed that even as we at Google try to retrain our own engineering workforce to use machine learning, it turns out that if you have simulations and data visualization front ends to play with some of these systems, you just speed up learning by like a factor of 10 instead of going back to the command line to learn some of the basics. So we can talk a little bit about that today as well. All right, so the first thing, let's start at the beginning with the data, right? Why might you want to visualize your training data, and what's special about your training data? One of the things that we started saying at Google is that whenever you start working with machine learning and you look at your results, and maybe your results are not coming out as strongly as you would wish, there is this innate intuition, or this, you're like itching to debug your machine learning model, right? One of the things we always say is, before you even debug your model, debug your data. And that becomes, it's incredibly important. I'm sure you're talking about a lot of that here in the class as well. Problem is, we don't have good tools to do that today. So we're starting to build, us at Google and other places, everybody's starting to think about what might be interesting tools for you to start to debug your training data, the data that your system is going to rely on. So we started to approach this from a data visualization perspective. So what I have here is a screenshot of the CFAR10 data set. Everybody familiar with that data set? Very simple data set of images, 10 classes, that's all. And so what I'm going to demo for you right now is a visualization we created. It's called Facets. And Facets is a visualization, right now I'm visualizing CFAR10. And all I'm doing, as you can tell, is I'm just looking at all the pictures. These are not all, it's a sample of CFAR10, of the pictures in each class. And I can very easily zoom in, and I can see what the pictures look like. I can zoom out. And even as simple as this is, it already starts to give me a window into what's happening with my data. One of the things I can see right away is that the hues are different, right? Something you may expect. So the top row here is airplane, and you can see that it has a ton more blue than, say, bird or cat or deer. And so does ship. That may be expected, right? Because I take pictures of airplanes against the sky, and I take pictures of ships against the water. Okay. But then I can start to play some interesting games. I can say, show me the same data set within each category, but now I want you to arrange this in terms of hue distribution, okay? So now I can start to see, okay, these are little histograms of my pictures per category, per hue. And voila, what are the bluest of the blue airplanes? Or there might be some interesting blue birds here. Okay, these are also against the sky. That's interesting. Let me see, I have some reds on airplanes. Okay, interesting. Just a very easy organic way to start looking at my data. I can also look for things like, okay, what are the classes of, in my data set that have the most, if you will, kind of equal distribution of hues. You get to things like ships and trucks and so forth. And you have these bulges of kind of earthy tones for the animals, right? Which makes sense. I can also start playing other games. So I can come here and say, okay, now give me a confusion matrix of my data. And again, the confusion matrix is going to pair each one of these rows is what the system thinks my image is, versus each one of the columns is what the humans have hand-labeled my image to be. So the good news to me is that right away I can see that the diagonal is the most populated set of cells. That's good, because that's where my system and the humans agree, right? And another interesting thing I can see here right away is that I have a couple of cells that are highly populated. I have this cell here, ton of pictures, and I have this other cell here, ton of pictures. And sure enough, my system is getting confused between dogs and cats, okay? So that already might start to give me some hints as to what I might want to debug about my system. Maybe I need to give it more images of cats and dogs, so it does better on those classes. Now keep this in mind. This is CFAR 10. This is kind of a hello world data set of machine learning. Everybody looks at this data set. Everybody benchmarks against this data set. It's been looked at by thousands of people, right? So we started visualizing this and we're like, oh, okay, so my system is very sure that these are not cats. So let's see what the cats are that my system is very sure are not cats. Interesting, okay, so I can see how like this guy here has big ears, maybe it's getting confused about that, all right. But then we started seeing some interesting things. I challenge you to find something in the bottom rows that is indeed not a cat. Anyone? A frog, yes. Look at this. This was hand-labeled cat, but my system is 100% sure it's a frog, and I have to give it to it. I think it's a frog. I don't think it's a cat at all. But why does that matter? It matters because just by giving you the ability to look at your data, you can start to see actual mistakes in your data, right? And again, this is a data set that thousands of researchers and practitioners use and benchmark against. And nobody knew that there were a couple of mistakes there. Interesting things, right? So again, just creating the ability to look at your data very easily can get rid of a lot of headache for you. So that's Facets. And we open sourced Facets. So Facets is available for anyone to use. And it's been downloaded a bunch of times. You don't have to use it for machine learning. It's a visualization tool for any kind of faceted data set. So you can use it for anything you want. And here at MIT, people have started using it. So Joy, for instance, at the Media Lab was using Facets to look at racial bias, racial and gender bias in facial recognition systems from industry. And she was using the visualization to make the point that the category of women of color was the category that the system would consistently do worse at. All right, if I have time, I'm gonna come back to the what if tool. The only thing I'll say about this tool is that it's another open source tool that we created that allows you to probe a machine learning model as a black box and to probe for things like machine learning fairness, different concepts of ML fairness. If we have time, we'll come back to this. All right, so we just talked about the importance of looking at your data. Now let's talk a little bit about what can you learn when you're looking at your model. Sort of how is your model understanding the world? How is it making sense of very, very high dimensional data? So I'm gonna walk you through a very quick exercise in high dimensionality. So a warm-up exercise. MNIST, yes, MNIST, everybody familiar with MNIST, right? Another Hello World data set of machine learning. And I'm going to start pulling us over to the world of visualization again. So think about each one of these images as a very high dimensional vector. How might I think about that? All I'm gonna do is I'm gonna count the pixels, and depending on the color of the pixel, I'm gonna give it a value from 0 to 1. 1 if it's all white, 0 if it's black, something in the middle if it's a gray. I end up with a vector. Boom, I transformed an image into math. That's great. Now I have a great way to compare these images. All right, so then we created a visualization to actually look at this. So this is another tool that's open sourced by Pear. And this is called the embedding projector. And now what we're doing here, we're looking at MNIST in high dimensional space. Okay, so this is a 3D projection of the MNIST numbers, okay? All I did here, since I have ground truth, I colored the numbers by the ground truth, okay? And the projection I'm using here is t-SNE. It's a nonlinear projection. It does really well in keeping track of local clusters. It doesn't do very well at all in understanding the global structure of things, but locally, it's very good. So, what do we have here? The good news is that we have clusters. That's a good starting point. And we have space between clusters. So that's really good because it tells me that somehow these categories are being pulled apart from each other. We also have, so let's start playing with this tool. It lets me rotate in many different ways. I can zoom in and out to look more carefully at things. I can also click on things. So basically, just so you know what's going on here, I'm setting up a demo using the same tool that shows you how a visualization like this can work in a real system, in a large system. The system I was showing you before, the data I was showing you before was MNIST, right? Very easy toy example. What I'm showing you now, and this is, it's taking its time to get to the t-SNE projection. It's calculating t-SNE, it's calculating all the clusters in this data set. And I want to be able to interact with it. That's why I'm taking my time, and I'll talk to you while this is working in the background, okay? So we're gonna let this do its thing. It's gonna run in the background. I'm gonna try to get it not to distract us completely. Meanwhile, let's talk about interpretability in a real-world scenario. So a couple of years ago, Google came out with something called a multilingual neural net translate system. What does that mean? It means that up until that moment, whenever you wanted to use neural nets to translate between two languages, you had to train a model on a pair of languages. So I trained a model between English and French, French-English. I trained a different model for English and Japanese, Japanese-English, okay? So it was all based on pairs. For the first time, Google came up with an architecture that let you ingest multiple languages and translate high-quality translations into multiple languages, okay? And that was a revelation. It was quite a feat. And so that's called the multilingual translation models. There's another thing that was interesting in what these systems were doing. Somehow they were able to do what we call zero-shot translation, okay? And so what that means is that imagine I have a system that is ingesting a bunch of sentences that translate between English and Japanese, Japanese and English, and it's also ingesting a bunch of sentences that translate between English and Korea and back and forth, okay? Somehow this system was able to also do Japanese to Korean and Korean to Japanese without ever having seen a single example of a sentence that goes straight from one to the next, okay, from Japanese to Korean. So one of the challenges, one of the big unknowns is that the people building these systems, they weren't sure how is the system being able to do this with high quality translation. High quality translation is extremely hard to get. It's extremely nuanced. And so how is it doing that? This was the data that we decided to visualize to actually start answering that question, okay? It turns out that between the encoder and the decoder, there is an attention vector in the middle, and this is the data that we were going to visualize, all right? The question in these researchers' minds, these are the people who were building the translate system, was imagine I have a space with multiple languages, an embedding space, a very high dimensional space of language. What were these multilingual systems doing? Were they doing something like what's here on the left, where they would resolve the space by keeping all the English in one corner, keeping all the Japanese on the other corner, and keeping all the Korean in another corner, and then just mapping between these spaces for translations? Or was the system doing something more like what you see on the right, where it's way more messy, but they're bringing together these multiple languages, okay? And so why does this matter? Why does it matter if it's one way or another way? It matters because if what the system was doing was mixing up the different languages in the same high-dimensional space, it had a very specific implication, which meant the system didn't care as much that one string said, for instance, home, and another string said casa. It knew that these two strings had the same semantic meaning. So if it was co-locating these very different strings from very different languages in the same high-dimensional space, it meant that it was paying attention to the semantics, the actual meaning of the words. And that matters because that then tells us that these are the first indications of a universal language, okay? And so, but we had no way of knowing, so we decided to visualize. And how might we visualize this? Imagine I have a sentence that says something like, the stratosphere extends from 10 kilometers to 50 kilometers in altitude, okay? What does that look like in high-dimensional space? It looks like a bunch of points where some points are going to be closer together, like the 10 and the 50, maybe, because they're both numbers, okay? So again, location has a specific meaning here in high-dimensional space. And then what we do with the visualization is we connect these dots. And so that is my sentence in high-dimensional space. It's the path of my sentence. Okay, so now I have my sentence in English. What does this look like when I have when I have a translation? Does it look like this, where I have my English sentence in one corner and I have the Portuguese version of that sentence on another corner? Or does it look more like something like this? Okay, and so this is what we're trying to find out. So the visualization for this, let me see, is actually this here. So what I'm showing here, again, we're back in the embedding projector, and I'm visualizing a multilingual system that takes in English, Japanese, and Korean. I am coloring each one of those languages by a different color. So English is blue, Korean is red, Japanese is yellow, okay? My question to you is, as messy as this looks, do you see a big neighborhood of red and a big neighborhood of blue and a big neighborhood of yellow? No, right? So that right there was our very first indication that something really interesting was happening, because we started to see clusters that had the three colors together, okay? And so the thing that I was hoping to show you, but I don't know that I'm gonna be able to show you. Let me see if I can. Oh, maybe I'll show you like this. So if I do a search for stratosphere, will it, oh, it just did a bunch of stuff here that is not helpful. I'm going to try to drag it all the way here. Do you see this little cluster here? The stratosphere with the altitude between 10 and 50 kilometers, okay? Ignore all of this junk here. This is not supposed to be there. But this is what I care about. If I look at this cluster, okay, and I look at the nearest neighbors, these are the nearest neighbors here that I'm mousing over. The 3 languages are here, okay? And my nearest neighbors for that sentence in English, both in Japanese and in Korean, are all in that cluster, all right? So that, in fact, did you see I just clicked out and you see the cluster has 3 colors here? So that was our indication that this was actually the beginning of a universal language. This system was actually being able to coalesce the 3 spaces of 3 different languages in terms of semantic meaning. Now, keep this image in mind, and I want to show you a sister image, a visualization of a sister system. This system here. It's the same kind of visualization, but this is a system that takes in English, Portuguese, and Spanish, okay? What do you see that's different here? Separated, right? I see a big neighborhood of red there. And so we saw this and we're like, wait a second. We thought there were indications of a universal language going on. What is that doing there by itself? So we did a statistical analysis for quality of translation, and we found out that the sentences in this cluster that was being pulled apart, the translations were all bad, low-quality translations, okay? So what does that tell us? It tells us that the geometry of this space matters, that if you have a multilingual system, kind of in the case Google had, if your system looks like this, that's bad news. That means that your system is not being able to cluster in the right way, and it's having difficulties, and it's going to do a bad job with translations, okay? So again, visualization here, not only to give you a sense of the landscape of what's happening in these massively high-dimensional spaces, but also giving you a clue of how to start debugging your system. Maybe you need more training data in Portuguese. Maybe it's something else, but you have a problem, okay? So this was really exciting because it was the first time anyone could see kind of like an MRI version of this neural net. And the fact that it was functioning at the super high level it was functioning for a language. A couple of other things I want to show. The same visualization can let us to understand things about our own language that I think are very interesting. So this is, again, the embedding projector. And you can, one of the things I didn't demo today is not only do you have these projections like T-SNE that you just saw, or PCA, you also can create custom projections. You can say, let's look at the English language. So imagine each one of those dots is a word in the English language, okay? And now, what I want to understand is the notion of biases in our language, okay? You may be familiar with papers like this one about word embeddings and the fact that you can do calculations in the direction of certain vectors. So you can say, oh, look, in word embedding space, if I take the direction between China and Beijing, if I take that direction and I follow roughly that direction from Russia, I'm going to end up in Moscow. Okay? If I follow that direction for Japan, I'm going to end up in Tokyo, and so on and so forth. So there are these meaningful directions in word embedding spaces that are incredibly powerful. So now let's use that to start visualizing language. What I did here is I went to the embedding projector that you just saw, and I looked for the word book, okay? And then I filtered all the words by the 100 top nearest neighbors to book. So I have words like biography and publishing and manuscript, all the nearest neighbors to book. But then I said, okay, now I want to see these words along the following projection. I want to give an axis that goes from old to new. So the closest, the more to the left a word is, the closest to old it is. So let's see some of the words. I have poem, manuscript, author, story, okay? Closest to new, here on the right, I have company, publications, theory, mind, creation, volume, okay? Okay, interesting. Now let's look at a different set of words. My axis now is man to woman, and my focal word, my anchor word is engineer, and all of its nearest neighbors. So I can tell already the engineer is closer to man than it is to woman. By the way, the y-axis doesn't mean anything, it's random. Just pay attention to the x location, okay? So closer to man, I have engineers, engineering, electrical, electronics. I have a really interesting word here at the bottom, but I can't. Look at the bottom, I can't point. Michael. Michael is one of the top nearest neighbors to engineer. That's crazy. Okay, and then close to woman, I have journalist, lawyer, officer, diplomat, writer, poet. Okay, let's keep going. My new anchor word is math, between man and woman, next to man, computational, arithmetic, flash, computation, physics, astronomical, so forth. Next to woman, psychology, instance, procedural, art, educational, library, and so forth. I changed my axis now. It goes from Christian to on the left to Jew on the right. And my anchor word is moral. So close to Christian, Christian, beliefs, religion, faith, religious. Closest to Jew, intellectual, psychological, serious, educational, sexual, liberty, ethical, so forth. Okay? Why does this matter? It matters because it starts to me, this is kind of like the canary on the mine about, this is just language. The data set here, remember we were talking about training data being incredibly important? Word2Vec, which is this data set, it's from hundreds of thousands of publications. It's just how we use language in the real world, okay? So when you are training your machine learning systems based on language, one thing to keep in mind is the fact that you're training on a biased data set. And so being aware of these biases can actually be incredibly important. And hopefully being able to use tools like visualization tools starts to give you a way of even becoming aware, acknowledging, understanding, and hopefully trying to mitigate some of these effects. I think I'm going to stop here and open up for questions. Thank you. Any questions?
How do you place words when they have multiple meanings?
That's an awesome question. If you had a word that had multiple meanings in, say, a projection like this, it would probably show up in the middle, which would not be very illuminating. Another thing that happens on the embedding projector is that you may have a word that is very, very strongly, so let's talk about a concrete example, the word bank, okay? The word bank can be a financial institution, it can also be a river bank, right? If my corpus of data that I trained on is on financial news, there's going to be a very high pull towards financial institution vocabulary, right? And I will see that bias in my data set. Hopefully, what also shows up, if my data set is broad enough, is that when I highlight that word in the visualization, here I was filtering, but imagine I have the entire language, okay? Let's say I highlight the word bank. It definitely lights up all of the financial, institutional vocabulary that's highly connected to that, but it also lights up stuff like river elsewhere in the visualization. And that is one indication where you're like, oh, interesting, there are these disparate, very separate clusters here. Maybe there's something there. Maybe that's one indication that you have these words with multiple meanings.
With the language stuff, is there a mathematical or physiological reason why multiple languages get clustered together rather than a complete separation between languages? Have you guys asked that question as to why it prefers that mode over clean separation?
So part of what we were trying to understand was what mode at all it was in. We had no clue. We were literally like, if it separates, that's fine. If it doesn't separate, that's interesting. Literally, we were like, just give me a telescope so I can look into this world and see what it looks like. The system was working really well, so it was more of a curiosity of trying to understand how is it working so well? What is it doing that it can get to these very high quality translations from no training data on specific pairs, right? It was more that kind of question than the, oh, we think it should do this or we think it should do that. It was literally like, what is it even doing that it works this way? Once we got to that set of questions, another set of questions that came up was like, well, here's a system that's not working so well. Why is it not working so well? And so that was the point that I was trying to make when I showed, oh, look, this system between English, Japanese, and Korean that was working really well, that looked like this, okay? Now let's look at a system that was not working so well, and it's a sister system. Oh, okay, here's a clue about why maybe it was not working as well. Does that make sense? Yeah, sure.
For these types of biases that could crop up change, I mean, there might be different biases for each culture and the language that is with it, and having a difference between those, could that interrupt the quality of the translation then?
In terms of biases?
I mean, like if one language has a very different set of biases, so you can make this word map for that language, it might look different than a word map.
Oh yeah, I think one thing that would be wonderful that I don't know that anyone has done yet is exactly what let me know if I'm understanding your question correctly. I think it would be wonderful to compare embedding spaces of different languages, right? It could be that in English, we have a set of biases that maybe don't exist in Turkish. I don't know. And even trying to understand, for instance, what are the nearest neighbors of a given word in English versus nearest neighbors of a given word in French? How much does that set of, how do those embedding spaces differ? I think that would be incredibly interesting. If we're talking about translation, one very complex issue that touches translation, word embeddings, and biases is what happened, what used to happen. Now Google started addressing this. What used to happen when you went to Google Translate and you said something about a doctor and a nurse. The doctor is coming and the nurse will see you, okay? So when you were to translate between languages that have gender, like English, to languages that don't have gender, like Turkish, it turns out that so imagine it going the other way around. Imagine I have that sentence, the doctor is coming to see you, in Turkish, and I am translating that into English on Google Translate. Google Translate would translate it into, the doctor is coming to see you, he will look at your exams. There was an assumption that it was a he. If the word being used was nurse, there would be an assumption in English that the pronoun following nurse would be she, okay? even though the original, the source language, had no notion of gender whatsoever attached to any of those words, right? And so Google had to proactively work out a solution where it realizes it's coming from a non-gendered language to one that has biases in terms of professions and gender, and give users a solution like, oh, the doctor is coming to see you. He/she will talk to you next, or something like that. So these are the kinds of biases you want to be aware of and try to mitigate, work around.
Yeah, but what's the philosophical basis of mitigation, right? You're sort of arguing that statistically these decisions are made by looking at the data. Let's say we know that nurses are 90% female, right? That's just the data. It's not a bias or an unbiased. So if you're looking at the mappings of the translation, it should pick up an order of magnitude disparity. So you're sort of making an editorialized political philosophical decision as to what correction you make, right? And now it's just reflecting essentially your or Google's or whomever's personal bias and injecting a correction to overwhelm the statistics. Now,
that's a very interesting point, because part of what we're trying to do is we're trying to understand what is the intent on the user side. So as a user, I want a translation to my problem, which is I see a sentence in Turkish and I have no idea what it means in English. If all you're giving me is the top hit from a statistical distribution, you're giving me a very specific answer. You're not giving me all the possible answers to my translation problem as a user. As a user, it is important for me to know that the translation to that sentence could be he, but it could be she, right?
sure, I mean, in a way, right, transparency would argue you could pick, do I want a politically correct translation, do I want...
Or do I want a distribution? Do I want you to decide for me what the translation is? Again, like if I don't know the language I'm translating from, right? I want to understand what are the possibilities in my own language I can understand. So therein lies the dilemma. It really depends on what do you think the user's intent is, and how do you work with that? But yeah, to your point, absolutely. Again, we're back to the fact that the data is skewed. Absolutely, it is skewed, right? And to your point, it reflects a certain reality.
Let's thank Fernanda one last time.
Thank you.